Greetings. This is the next video on area in the sequence for Calculus 1 / AP Calculus AB, and this comes after the area videos for like the ones entitled area between two curves. Those videos were about vertical slicing, and I didn't mention that there is another way of slicing the areas, but there is, and that is namely horizontal slicing. And we will talk about that in this video. Let's get into it. So, when to use it? Well, first, horizontal slicing gives us a new way of finding area between two curves. Not just area between two curves. You can find the area inside of just one curve with just some limits. You can simply do that. And you can use horizontal slicing for that, because in the past we have been using vertical slicing, but you can use horizontal slicing for that, and also when you have two curves. You can use horizontal slicing for everything you would use vertical slicing for. Previously, our area finding methods that involve definite integrals, at least, excluding Riemann sums and trapezoid rule and stuff, involved vertical slicing. This new method utilizes the concept of horizontal slicing. Nothing wrong with vertical slicing. Vertical slicing is awesome, and we're still going to use it a lot. Horizontal slicing is not going to replace vertical slicing. However, it's just another option, because there will be times when vertical slicing cannot be used to find an area, or vertical slicing makes the area very difficult to evaluate, and in those instances, horizontal slicing comes in handy. And so it's useful to know how to do both vertical slicing and horizontal slicing. Okay, so let's get into this horizontal slicing thing. And before we actually, I'm not going to do any problems in this video, actually. I'm just going to talk about why horizontal slicing works and the formula and things like that. The problems, the practice problems, will come in a later video. And so let's talk about why this works. What exactly is horizontal slicing? So we have a coordinate plane, right? Typical coordinate plane. And let's just imagine that we have a parabola. This is going to be like a horizontal parabola. Let's say it's like this. This is a horizontal parabola. And it's inside of the family of these functions. It's not exactly x equals y squared, of course, because there's like a shift here, but that's beyond the point. It's in the family of x equals y squared functions. And let's say that we were asked to find the area between let's call that x equals 2 and x equals 5. So that would be like here. So how would we even do that? How would we find the area between those two regions? Which that area would be all this yellow. How would we do that? And so from what we've learned so far, utilizing the definite integral, which actually gives you an exact area, so it's the best method to use. Using the actual definite integral, what you would probably do is you would rely on the vertical slicing method. You would, come up with infinitesimally small, super small in width area slices, vertical slices, and then use the definite integral symbol to sum up all of those slices, and you get your answer, right? That is probably what you would do, because that's what we've learned so far. However, there is another way of doing that. And that would involve taking horizontal slices. Which is it like better to do that than to do vertical slices? It might just depend on what you like. But so these would be once again infinitely small, infinitesimally small horizontal slices, and then you would add them all up using the definite integral, and you would get your answer. And so now we're relying on slicing horizontally instead of slicing vertically. And this simply just makes it easier to do the problem sometimes, or you might not be able to do it at all using vertical slicing, and so you have to rely on horizontal slicing in some instances, perhaps like maybe this one, coordinate plane, and we have a curve like, how about a curve like this? I just have an idea, like that, and then like that, and yeah, imagine it's like symmetric, I guess. I don't know, it doesn't really matter, but, and they want you to find, let's say that's -2, this is 2, they want you to find the area in between -2 and 2. Of course, that would be everything in green. Now, how would you go about doing that? If you were asked to find the area vertically, or if you just didn't know what to do, so you said, I'm going to find the area for vertically splicing. So if you did that, then you would run into a slight problem. I mean, it wouldn't prevent you from doing it, but you'd just be like, oh, yikes, great. We have a top curve here of that function, and then on the other side of the y-axis, you have a different top curve. I shouldn't have drawn the curves in the same color, probably, but there you go. So, we have the top curve of the same color. That's not good, right? So there you go. I drew over that. So, but if you see for the first region on the left of the x-axis, the top curve is the black one, and on the second region to the right of the did I say x-axis? I mean y-axis. To the right of the y-axis here on the second region, we have a region that has the red curve as the top curve. So, what that means is that you're going to need two different integrals. Great, right? Two different integrals. So, whatever the black top curve is, black minus red, and then plus integral red minus black, which isn't good just because, well, it takes more work to evaluate two integrals. If you were to slice this horizontally, which is an option, if you were to slice this horizontally, right, all of a sudden then, you wouldn't have to worry about top curves and bottom curves. Top curves and bottom curves don't apply in horizontal splices. Well, they ideally do still. You can think of it as a top curve and a bottom curve for the moment. So because, let's just pretend that that top curves and bottom curves actually do, they still apply. What is the top curve and what's the bottom curve? Well, you would have to turn your device or your monitor or whatever you're viewing this on, you have to turn it sideways, right? Because the top curve is on top, should be on top of your slicing lines. So it has to be the top curve and the bottom curve, they have to be perpendicular to the slicing lines. So you would have to turn your device or your monitor or whatever to the side so you could see what the top curve and the bottom curve would actually be. Or you could also just turn your head. That would also work. And when I do that, well, the top curve is actually the curve on the right. The top curve is the curve red if you rotate it to the left, which it really doesn't matter exactly what direction you rotate it to. Well, actually, I mean, it does matter in the grand scheme of things because then you'll get a negative answer. But basically, like when we did the top curve, we said the top curve comes first because the top curve would be a positive number, ideally, because it's above the y-axis. Above the x-axis. Everything above the x-axis is positive. Everything below the x-axis is negative. So you should start with positive first, and then subtract the negative, and then you'll get a positive number, because positive minus negative equals positive. So when you rotate it, you kind of want the right to be on top. The curve on the right to be the so-called top curve. So your goal then would be to have the curve on the right minus the curve on the left, because that would get you a positive number. Right minus left would get you a positive number. And so your so-called top curve and bottom curves, when you rotate your head or whatever, your top curve then becomes the curve here on the right. Bottom curve becomes the curve on the left. And so now you only need one integral. You just need integral the red one minus the black one. That's all you need. So, what does this look like? What does this mean for our formula? This is what our formula now looks like. So there's some things that need to be noticed. Our formula is in terms of y now. Our formula is in terms of y. And so, that means that, for example, I said that in my first example here on the graph, x equals y squared. I said that's what the function was. Yeah, it is x equals y squared. And it's important that we have it in terms of y, because if we are going to solve for the area using horizontal splicing or horizontal slicing, if we are going to do that, then we need it to be in terms of y, because that's what the formula dictates. And also dy, which means you need to be integrating with respect to y. So your variables need to be y's. So it has to be in terms of y. So if they give you a graph like this and say, this is y equals square root of x, or something. Although square root of x, they would have a domain thing, right? They wouldn't have any of this here, because they would have not a domain, a range limit on it. So you can only have numbers for the top half of the graph, only things above the purple line. Anyway, but pretend with me that they give you this, y equals the square root of x for your graph, and they ask you to find the area. You would have to first find y equals the square root of x. You have to solve for x. You have to get it in terms of y first. That's important. The formula requires everything be in terms of y. And then your a and b, those also have to be y coordinates. Anyway, you'll see how the formula is used and how it's different from the vertical slicing formula when we get to the example problem video. Anyway, just wanted to introduce you to why it works. And usually I'm not going to show why it works before I do the example problems, because I just care so much about showing how to do it first. But for something like this, which requires a lot of visualization, and oftentimes in order to solve an example problem, you will have to graph it first before you can solve it to see how you're going to solve it. You need to plan out that part. So just knowing how your formula actually works and why it is as it is, knowing that kind of helps you plan out what you're going to do, how you're going to set up your problem, and how you're going to solve it. Okay, and here's the formula also. The two purposes of this video. Example problem video coming up. Okay, there you go.